Have you ever wished you had a universal translator? You know, like the one in Star Trek.
Like a real-time translator.
Yeah. We might actually be getting closer to that.
Closer. How so?
Well, because of something called the transformer.
Oh, I've heard of that. Isn't that some kind of AI thing?
It is. It's a neural network architecture that's making some big waves in artificial intelligence. It's already doing some pretty amazing things.
Like what? What can it do?
Well, for one, it can translate languages, but it can also write different kinds of creative content and even answer your questions in a really informative way. And get this, it does all this without needing someone to explicitly teach it how to do these things.
Wow, that's pretty impressive. So it's like it's learning on its own.
In a way, yes. It's learning from the data it's given, and the results are pretty mind-blowing.
So today we're diving deep into the research paper where Google researchers first introduced this transformer.
Oh, you mean attention is all you need?
That's the one.
Yeah, I sent you some excerpts from that paper.
You did. And we're going to unpack what makes this architecture so revolutionary.
And why it should matter to, well, everyone, really.
Exactly. So before we get into the nitty-gritty of the transformer, maybe we can set the stage a bit.
Okay, sounds good. What was the AI landscape like before this groundbreaking architecture came along?
Well, before the transformer, the go-to models for tasks like translation were RNNs and CNNs.
Remind me what those stand for again.
RNNs are recurrent neural networks, and CNNs are convolutional neural networks.
Right, okay.
And they were pretty good at certain things.
Yeah.
But they really struggled, especially when they had to deal with long sequences of data.
Like a really, really long sentence.
Yeah, exactly. Imagine trying to translate a complex sentence with multiple clauses. RNNs process information one word at a time, and that makes it really hard for them to remember what came earlier in the sentence.
I see the problem. So what was the issue with that?
It's like trying to follow a conversation where you can only hear one word at a time. You lose the context, the connections between ideas.
Oh, I get it. It'd be hard to capture the nuances of the language that way.
Exactly. And not only that, but this sequential processing also makes it difficult to train these models efficiently. You can't parallelize the computations, so you're stuck processing things one step at a time.
So it's like having a single-lane road when you really need a multi-lane highway.
Perfect analogy.
So slow, inefficient, and prone to forgetting crucial information. Not exactly the ideal scenario for AI.
Right, and this is where the transformer comes in and changes everything.
Okay, this is where I'm getting excited. Because I've heard that the transformer ditches these sequential approaches altogether.
It does.
And it relies on something called attention. Is that right?
You got it.
I've heard that term thrown around a lot, but I'm not sure I fully understand it. How does attention work in this context?
Well, it's like the researchers said in their paper title. Attention is all you need. That's really the heart of the innovation.
So how does it work? I mean, I get the general concept of attention, but how does it actually apply to a machine learning model?
Okay, think about it this way. When you're reading a good book, you don't give equal weight to every single word, right?
Right.
You focus on the key phrases, the emotional beats, the connections between characters.
Yeah, that makes sense.
That's essentially what attention mechanisms do in machine learning. They help the model focus on the most important parts of the input.
Oh, so it's like the transformer is learning to read like a focused and engaged reader. It's picking up on the nuances and connections that really matter.
Precisely. And the specific type of attention used in the transformer is called scaled dot product attention.
Scaled dot product attention. That sounds a little intimidating.
I know, it's a mouthful.
Yeah.
But don't let the name scare you. It's essentially a way for the model to weigh different parts of the input based on how relevant they are to the task at hand.
Okay, I think I'm starting to get it. Can you break it down even further?
Sure, imagine you have a question. Like, what's the capital of France?
Okay.
That question, that's your query. Now, you go to a giant encyclopedia to find the answer.
Okay, so the encyclopedia is like...
That's your key. And the value associated with that key, in this case, Paris, is the actual information you're looking for.
So the transformer is comparing its question, its query, to a database of information, the keys, to find the most relevant answer, the value. So it's like a super efficient research assistant.
Exactly. And what's really cool is that this allows the model to capture relationships between words that might be really far apart in a sentence.
Oh, right. Something those RNNs we talked about struggled with.
Exactly.
I'm following so far. Now, the paper also mentions something called multi-head attention. Is that just a fancier version of what we've been talking about?
It's kind of like having a whole team of detectives working on a case.
Oh, instead of just one.
Yeah. Each head is paying attention to different aspects of the input simultaneously. So they're bringing different perspectives to the table.
So instead of just focusing on individual words, the transformer is considering the bigger picture, like the context, the relationships, maybe even the emotional undertones.
You got it. And that's one of the reasons why the transformer is so powerful and versatile. It's not just memorizing words, it's understanding their meaning and their connections within the larger context.
This attention mechanism is sounding more and more like a total game changer. But what are its advantages over the RNN and CNN approaches? We already know it's probably more efficient, but what else is there?
Well, for one, the transformer is way more computationally efficient. It doesn't have to go through the input one word at a time, so it can process information in parallel.
Right, like that multi-lane highway we were talking about.
Exactly. Plus, it's incredibly good at capturing those long-range dependencies between words. The connections that might span across entire sentences or even paragraphs.
Yeah.
Traditional RNNs often miss those subtle but crucial relationships.
Okay, that makes a lot of sense. So it's faster, more efficient, and better at understanding complex relationships. It's like upgrading from a bicycle to a spaceship.
I like that analogy.
Yeah.
But there's still one crucial piece of the puzzle we need to address.
Okay, what's that?
Word order.
Oh, right. How does the transformer know which word comes first, second, third, and so on if it's looking at the whole input at once? That seems pretty important.
You're absolutely right. Word order is everything, especially for tasks like translation.
So how does it do it?
Well, the transformer uses something called positional encodings.
Positional encodings.
Yeah, it's a clever way to inject information about the position of each word into the model.
So it's like giving each word a little ID tag, something that says, hey, I'm the third word in this sentence, and don't you forget it.
Exactly. You can think of it that way. The researchers use the math involving sine and cosine functions to create these positional encodings. But the main idea is that each word carries information about its place in the sentence, even if the model is looking at everything simultaneously.
Okay, so we've got the attention mechanism, the multi-head attention, and the positional encodings.
All the key ingredients.
And what kind of performance did the researchers actually see when they put all these pieces together? Was it really as revolutionary as everyone says it is?
Well, get ready to be impressed. The transformer blew previous models out of the water.
Really?
It achieved state-of-the-art performance on machine translation tasks.
Just how much better was it? Give me the details.
Okay, so on the WMT 2014 English to German translation test, the big transformer model achieved a BLEU score of 28.4.
28.4.
That's right. And that BLEU score is like the gold standard in machine translation. Getting a score that high was basically unheard of at the time.
So it was a lot better.
Oh yeah, it was a full 2 points higher than the previous best model.
2 points.
And in the world of AI, that is a gigantic leap forward.
Wow. So what does that actually mean in practical terms? Are we talking about translations that are finally starting to sound human?
We are. Imagine a world where language barriers are practically non-existent, where you can seamlessly communicate with people from all over the globe.
Yeah.
The transformer is bringing us closer to that.
Yeah.
And it was not only more accurate, but also significantly faster to train than all those older models.
So faster, more accurate, and better at understanding context. It sounds like the transformer really lived up to the hype.
It did.
But did it do anything else besides translation?
That's what's so exciting about this architecture. It's definitely not a one-trick pony. The researchers also tested it on something called English constituency parsing.
What is that?
It's basically analyzing the grammatical structure of sentences.
Okay.
And guess what?
Yeah.
It aced that test too. And it did it even with limited training data.
So it's not just good at understanding and generating language, but it can also analyze and predict grammatical structure.
It can. And this versatility is one of the reasons why the transformer has sparked so much excitement in the AI world. It's not just a specialized tool, it's a powerful and flexible architecture. And it can be applied to a wide range of tasks.
So we can use it for all sorts of things.
We can. And to really appreciate how it works, we should take a look at some of the visualizations in the paper.
Oh, yeah. Those are really cool.
They give us a fascinating glimpse into the thought process of the model.
What kind of insights can we gain from these visualizations?
Well, they actually show how the different attention heads in the model learn to focus on different aspects of the input. It's like watching a team of experts work together,
Okay.
each bringing their unique skills to the table. Some heads might focus on long-distance dependencies, connecting words that are far apart in a sentence. Others might specialize in resolving pronouns, figuring out what he, she, or it refers to.
Oh, so we can actually see how the model is making sense of the information, how it's forming connections, and even how it's making inferences.
Exactly. Figures 3, 4, and 5 in the paper provide these incredible snapshots of the attention mechanism in action.
Right, right. I remember those.
And they're not just pretty pictures. They provide valuable insights into how the model is learning and achieving these impressive results.
This is all so fascinating, but I'm sure our listeners are wondering what this means for them. Why should they care about this transformer architecture?
That's a great question. The transformer isn't just a minor tweak to existing models. It's a completely new way of thinking about AI.
Okay.
And its efficiency, performance, and generalizability have opened up a whole new world of possibilities.
It sounds like we're talking about a paradigm shift here, not just an incremental improvement.
You got it. And while we're focusing on its applications in language processing, the potential applications actually go far beyond that.
Oh, really?
Think about it. The ability to find patterns and relationships in complex data is incredibly valuable, no matter what kind of data you're working with.
So it's not just about better translations or faster training times. It's about fundamentally changing how we build and use AI systems.
Exactly. And that's why the transformer is such a big deal. It's not just a technical innovation, it's a conceptual breakthrough. And it has the potential to revolutionize countless fields.
Wow, I need a minute to process all of this, but I'm definitely ready for more. What else can you tell me about this groundbreaking architecture?
Let's dive into some of the finer details of how the transformer actually works.
Okay.
It gets even more interesting, I promise. So one of the most intriguing things about the transformer is how it handles word order.
Word order.
Yeah, the sequential nature of language.
Right.
But it doesn't actually process the words in a strict one after the other sequence.
Yeah, we touched upon that earlier with those positional encodings, but I'm still not quite clear on how it all works.
Okay, well, let's think back to those RNNs we talked about.
Okay.
They read each word one by one.
Like following a breadcrumb trail.
Exactly. And that makes it hard for them to see the bigger picture, you know?
Yeah.
Like to make connections between words that are far apart.
Right.
And it also limits how quickly you can train them.
Okay, and the transformer bypasses all that by using attention to look at the entire sentence at once.
Exactly.
Kind of like taking in the whole view instead of focusing on each individual tree.
Perfect analogy. The attention mechanism allows the model to consider all the words simultaneously.
Regardless of their position.
Regardless of their position. It's like reading a sentence with your eyes darting back and forth, picking up different parts to get the full meaning.
Okay, that makes sense. But then how does it handle tasks like translation?
Ah, good question.
Where the order of words in the output can be completely different from the input.
Right. That's where the decoder comes in.
Can decode.
Yeah. The transformer uses what's called an encoder-decoder structure.
Okay.
It's kind of like other sequence-to-sequence models. So the encoder processes the input sequence.
Oh, okay.
Like imagine a chef is taking all these different ingredients,
Yeah.
combining them, creating this delicious dish.
Okay.
And the decoder takes that dish,
Okay.
which is really the encoded representation of the input,
Okay.
and then it generates the output sequence word by word. It's like a food critic describing the dish,
I love that analogy.
in beautiful detail.
So even though the transformer can look at the whole input at once, the decoder still has to generate the output one step at a time.
Exactly. The decoder is what we call autoregressive, meaning it uses the words it's already generated to predict the next word in the sequence.
Oh.
But here's the key difference. It has access to the entire input sequence through attention,
Okay.
which gives it so much more context for its predictions. Like the food critic can refer back to the entire dish, not just the bite they're currently tasting.
I see. So does the paper say anything about how this encoder-decoder structure is actually implemented in the transformer?
It does. Both the encoder and the decoder are made up of stacks of identical layers.
Just stacks of layers.
And each layer has two main sublayers, a multi-head self-attention layer.
Hold on. Multi-head attention, that rings a bell.
Yes. We just talked about that.
Yeah. That's the one that lets the model focus on different parts of the input.
Exactly, the star of the show. And the multi-head part just means it's using multiple attention heads.
At the same time.
All at the same time.
Yeah.
Each focusing on different aspects of the input.
So it's getting like a bunch of different perspectives.
Yeah. Bringing that diversity to the table.
Okay, and you said there were two sublayers, so what's the other one?
The second one is called a position-wise feed-forward network.
A position-wise feed-forward network. What is that?
Think of it as a way to kind of fine-tune the representations that are created by the attention mechanism.
Okay.
It applies the same transformation to each position in the sequence,
Uh,
adding like another layer of complexity and nuance.
okay. So it's like each ingredient's been combined by the chef, and now this is adding a bit of seasoning to each one.
That's a great way to put it. And the architecture itself is quite elegant,
Okay.
like how everything's connected.
Hmm.
The researchers also use what's called residual connections.
Residual connections, what are those?
Think of them as like little shortcuts
Shortcuts.
that help information flow through the network more easily.
Okay.
It allows the model to learn more effectively. So you're making sure all the flavors can blend and interact without getting lost.
I like that.
Another important detail is layer normalization.
Later normalization.
That helps to stabilize the training process, making sure everything cooks evenly, so to speak.
I'm loving all these culinary metaphors. It sounds like they really thought this through.
They did. They put a lot of thought into optimizing every aspect of the model. And they didn't stop there.
They didn't.
They spent a ton of time fine-tuning the training process.
Oh, wow. How did they do that?
Well, they used all sorts of techniques,
Like
something called label smoothing.
label smoothing. What's that?
It helps the model to be less overconfident in its predictions. It encourages it to consider different possibilities, which leads to better accuracy overall. It's like saying, hey, you might love this dish, but let's be open-minded.
Yeah, consider other perspectives.
Exactly. Another technique is called residual dropout,
Residual dropout.
and this helps to prevent overfitting.
Overfitting.
Overfitting is when the model just memorizes the training data.
Instead of actually learning.
Right. It's not learning the underlying patterns. So residual dropout randomly drops some of the connections between layers during training, and like making sure the critic is paying attention to everything,
Yeah. The whole experience, not just the presentation.
Exactly. All these techniques make sure the model can generalize well to new data it hasn't seen before.
Okay, so we've talked about how well it does with translation, but what about other tasks? Can it handle anything beyond language?
That's a great question. And the paper actually shows the transformer is quite versatile. Remember those impressive results on English constituency parsing?
Yeah, it was beating most other models.
Right. Even with less training data. And that's important. It shows the transformer can handle these structured prediction tasks.
It's not just mapping one sequence to another, like in translation.
Exactly.
So it's not just a language whiz, it can also analyze and predict grammatical structure.
It can. And it does it all while being more efficient and parallelizable than traditional models.
So impressive.
But here's the really exciting part. The transformer's success has basically sparked this huge wave of research, exploring its potential in other areas, even beyond language.
Like what? Give me some examples.
People are applying it to image recognition, speech synthesis, even music generation.
Wow, that's amazing. So it's not just limited to text.
Not at all. The key here is the attention mechanism. It can be used to analyze any kind of sequential data.
So the transformer is like a universal pattern recognition machine?
You could say that.
Ah.
And we're only just beginning to explore all the possibilities. It's still early days, but the potential is huge.
It sounds like it. This is all incredibly fascinating. It's starting to become clear why the transformer is such a game changer for AI.
It is. It really represents a shift in our understanding of how to approach complex problems using AI.
Moving away from sequential processing and embracing attention.
Exactly. We're opening up so many new avenues for creating truly intelligent systems.
It's exciting to think about what the future holds for the transformer and what other amazing applications we'll see.
Me too. And the best part is, the research is still ongoing.
It is.
Oh, yeah. The paper actually hints at some really interesting directions for the future.
Ooh. Like what? Give me a sneak peek.
Well, for one, they're looking at ways to make generation less sequential.
Less sequential.
Yeah, remember how we talked about the decoder generating the output word by word?
Mm-hmm.
Well, they were trying to figure out ways to make that more parallel.
So it could be even faster and more efficient.
Exactly. It could be revolutionary. They're also thinking about extending the transformer to handle other types of data,
Like
images and audio. Imagine combining all these different modalities into one super powerful model.
That's incredible. So we're talking about AI systems that can see, hear, understand, and even create like never before.
That's the idea. It really feels like we're at a turning point.
It does.
The transformer has opened up a whole new world.
Yeah.
And it's only a matter of time before we see its impact on all aspects of our lives.
This has been such a great discussion. We've learned about the limitations of traditional models, the elegance of the transformer, the power of attention.
And we've even gotten a little philosophical.
We have, talking about AI and the potential to unlock the secrets of the human mind.
It's been a journey.
It has. But before we wrap things up, I want to leave our listeners with a question.
Okay.
How might this transformer architecture be used to solve problems beyond language processing? Think about its ability to find those patterns in complex data. What other applications could benefit from this?
A lot of them, I think. It's definitely a question worth considering.
It is, especially as we enter this new era of AI.
Thanks for having me on. It's been great exploring these ideas.
Okay, I think that about wraps it up for today. We've covered a lot of ground, but what are your final thoughts? It's kind of amazing when you think about it. The transformer's ability to focus on the most important parts of the input.
Yeah.
It's like how our own minds work.
That is a really interesting point. And, researchers are actually starting to explore that connection more deeply.
Yeah, what have they found?
Well, think about it. Our brains don't process information like a computer, right? We don't just go step by step.
No, we jump around all the time.
Exactly. We're constantly making connections, weighing different pieces of information based on what's important.
We're doing it right now.
We are. So attention, it's not just some abstract computer science term. It's a reflection of how our own minds make sense of the world.
Wow. So you're saying that AI is helping us understand ourselves better?
I think so. It's like we're holding up a mirror to ourselves.
A mirror made of algorithms and data.
Exactly. And that's one of the most exciting things about working in this field.
It's not just about building smarter machines. It's about expanding our understanding of intelligence itself.
You got it. Both artificial and human.
Well, I think it's safe to say we've covered a lot of ground today. We've learned about the limitations of those traditional models, the elegance of the transformer architecture, the power of attention mechanisms.
We even got a little philosophical there.
We did, talking about AI and the potential to, maybe unlock the secrets of the human mind.
Who knows what the future holds?
That's the exciting part. Before we go, I want to leave our listeners with something to think about.
Okay, fire away.
How could this transformer architecture, how could it be used to solve problems that go beyond language processing?
That is a great question.
Because if you think about it, its ability to find patterns, relationships in complex data, that has to have applications in all sorts of fields.
Absolutely.
Yeah.
It's something to really consider as we move into this new age of AI.
It is. Well, thanks for joining us on this deep dive. It's been a pleasure exploring these ideas with you.
It's been fun.
And to our listeners, until next time, keep learning, keep exploring, and most importantly, keep asking those big questions.